Oh, hey, yay, we're live. So I will just organize the slides a little bit, and then we can start in like 1 minute. I also need to share the link everywhere, so that will take me a couple of minutes. All right, let's go search for the YouTube link again. Great, I will add it on Telegram. Shared it everywhere. Awesome, ready to go. I will just share my screen and we can start. I always need to move the screen a little bit for this step. All right. You should be seeing some Google slides. Perfect. Awesome. So welcome to the first part of the Finality workshop. We will be reviewing today the Casper Friendly Finality Gadget, or FFG. So first of all, I want to spark some very small discussion here. So the reason why this is called a gadget is because it's not an independent consensus algorithm like fork choice, the one that we saw last week, or I don't know, maybe it was 2 weeks ago. It was completely independent. It doesn't need anything else to provide fork choice. However, the goal of Casper is to provide finality to an existing consensus algorithm. So basically, this is something that you add on top of, for instance, fork choice. So my question, which is something I want to open to you all, if you're willing to participate, is first of all, what is finality? And second, why do we even need finality? Like with what we saw a couple of weeks ago, we already have a functioning blockchain, right? We already can design of the current version. So what do you think that finality is, and why is it important?
I think without finality, the process has to start from the genesis, and with finality, the validation starts from the last finality validated block or chain point.
Interesting. So there's efficiency there, right? Like fork choice basically assumes that you will start from Genesis, which is extremely costly. Like if I needed to go to Genesis and calculate the whole tree of weights to choose the correct fork, that's extremely costly, and that's one very good argument. Anything else?
Um, I, I think it helps to like from the word finality, it helps to um, ensure that transactions are irreversible. Because I think with there are different types of finality. There are the ones that you can be sure, and there's one that you have high probability of finality, but both of them still ensures that you can't go back in time to do things because now you have a point that you can trust. And like you said, moving forward, you can check against your last sure block or last final block, so to say.
Yeah, of course. And there's a famous post around. I don't remember if it was a post or if it was a paper actually, because I read this a long time ago. That's called "It's All About the Guarantees," and in this case, that applies. Like it's all about the guarantees of how much you're willing to guarantee the blockchain users that a block will not be reverted, and that has real life utility, right? Not only efficiency. Because like if you do a transaction, for instance, you pay someone using a stable coin, you want them to be sure that they receive their payments so that they can start doing their work. You need some level of guarantee that it will not be reverted in the future. With fork choice, we already have an advantage there because we didn't do the formal proof, but we know that like whenever you add a new block, reversing a previous block is exponentially more difficult because you will need to change votes on older blocks. So on the one hand, that gives you some level of guarantees, but this gives you another level of guarantee, which is this will never be reverted. And I say quote unquote, and we will see why later on, which is very related to what you said, Gospower, which is there's different kind of finalities or different kind of guarantees, actually, because here we will only have one kind of finality, but the finality will provide different guarantees depending on assumptions. But that will be the conclusion of the workshop. So we will get there. So basically, like, those answers were perfect. Those are both of the things that I was wanting to reach, which is efficiency, which is not starting from Genesis, and also real world utility, which is not having something reverted. So yeah, let's just continue with it. Thank you for the answers. So this is kind of an introductory section, which is the last time we discussed attestations. And we discussed attestations specifically related to the roots of the blocks that were being voted for in fork choice. What we will see this time is that in finality, we vote for checkpoints instead of the roots of individual slots. So basically, as we saw last time, an epoch is divided in 32 slots, right? In fork choice, what we did was vote for each slot, which was the correct block or the correct bifurcation. Here, a checkpoint voting lasts a whole epoch, right? And during the whole epoch, what we're trying to vote is which is the current checkpoint we want to finalize. So in all of the 32 slots, we will try to be voting on the same thing, which is kind of different to what we did on fork choice, where we were voting different things each slot. For exclusively efficiency reasons, we share the attestation data message with both fork choice and finality. We could have them propagated in different messages, but if we are having one attestation per slot, it doesn't make sense to send two different messages. So we just like piggyback data on that message. So slot and index is basically like general data. This is the slot where the attestation happens. This is the index of the validators that's performing the vote. The index of the committee that's emitting the data. And then we have these three things that are the beacon block root for the slot, which is a fork choice vote, which we saw last time. And then we have source and target, which will be our votes. So you maybe are asking yourself, okay, what are source and target? The short answer is that they are checkpoints. The checkpoint is basically an epoch and the root of the block that corresponds to that epoch. The epoch is basically the number. And the only thing that we are missing now is, okay, what's source and what's target? We'll see that in a couple of minutes. So we actually are not voting for one checkpoint. We're voting for two slightly different ones. Okay. Like the most intuitive one is target. Target is, okay, it is trying to say to the others what's the current checkpoint according to me. Oh, and also, I don't know if I clarified this, but the checkpoint is the first slot of each epoch. So when we are traversing all of the slots of an epoch, we are voting which is the correct checkpoint for this epoch. At any point, if there's any questions, feel free to just interrupt, start talking. Don't worry about it. Okay, so we will do something to provide certain level of safety. We will do something that's called two-step commit, right? Because intuitively, what we could do would be just to propagate the root of the checkpoint that I think is the current one, and I could call it A.
Yeah.
That's it.
Sorry.
Go ahead.
Sorry, you said that the checkpoints is the first slot. Can you go over that again? I didn't really get it.
Yeah, I'll pull a couple of slides afterwards, but I have this graph that may be useful. So this is an epoch, right? And basically an epoch is 32 slots, right? So each one of these squares is a slot. And the first slot in this epoch, it's called the checkpoint. And in the next epoch, this will be the checkpoint. Each epoch has one checkpoint, right? When we say voting for a checkpoint, what we are voting is to say, hey, because an epoch and a slot are units of time, right? They are numbered. Like I have the slot 0, the slot 1, the slot 3. but their contents is kind of variable. Like depending on what each of the validators vote, they can be block E, block A, block D, whatever. The checkpoint number is the same as the epoch number. Like for epoch n, we are saying that we will call it the checkpoint n, and the checkpoint n corresponds to the slot 32n, because there's 32 slots in each epoch. In this case, for the epoch n+1, we have the checkpoint being the slot 32, and this should have a parenthesis here, n+1. So basically, throughout, like when we are here, we're voting for this one, and when we are here, we're also voting for with this one, and when we are here, we're also voting for the contents of this one, and that will be our target checkpoint. We will try to agree on this.
Yeah.
And the reason why we do this is because, like, for fork choice, the only thing that we cared about is which is the correct fork. For finality, what we want is to reach a certain level of consensus and count how many people voted on that. So I'm spoiling a little bit of what we will talk later on, but the goal is to say, hey, if 2/3 of the validators agree that this is the checkpoint, then I will consider it. If we don't have two steps, I would consider it final. I would just say, hey, 2/3 of the network agree. And because of, like, these are results of proofs for all of the Byzantine consensus algorithms, 2/3 is enough guarantee that that you have a working network. And with that, you can say, okay, this is final.
But is it after? It should be after the epoch is done, right? Because if it's in the epoch, it can be like still.
Of course. So the idea, that's a perfectly good subtlety. Like we throughout this epoch, we will be voting for this one, but this will only be finalized, and quote unquote, because there's two steps that I will talk in a minute. But that only happens when I transition from this slot to this slot. That's where, if you remember correctly, when I go from slot to slot, something happens which is called slot processing. But when I do this traversal from epoch to epoch, I have epoch processing. And one of the things that's included in epoch processing is, well, justification and finalization, which is basically the processing of finality. Does that answer the question?
Yes.
Perfect. Okay, let's go back then. So we actually will divide this into two steps. If we think this from the perspective of one node, which is represented by this cursed smiley, basically I will, when it's my turn to perform an attestations, I will propagate the root of the checkpoint that I think it's the current one, and this will be called the target, my target checkpoint, which was here in my attestation, right? So I will emit a vote for that, and I will say to everyone, hey, I think that this is the target checkpoint, and I will also get the votes from every other validator. That will happen across all of the epoch. So basically, imagine that I have a small network of 4 other validators, 5 in total, and I get 4 votes. This vote says that the current checkpoint is R1, same for this, and same for this. But this other one says that the target is R2, right? So we have 2/3 of the network saying that they agree on which is the current checkpoint, which is enough for me. For me, 2/3 is the magic number. So what I will say is that I will declare this. I won't declare it final yet, and I will say why in a minute. I will justify that checkpoint. And justification just means that I will commit to locally not changing that. I will consider that the starting point of my fork choice algorithm, and I will ignore everything that's outside of that, at least for now. And if something like, hey, like afterwards the whole network changes opinion and there's another fork, but basically I will commit to not changing that at all, especially for fork choice. But I will not finalize it yet. And why is that? Well, I will perform a second step then, which is I will say, hey, not only this is my target checkpoint, which will be my next vote as well, but this is my current, like my latest justified checkpoint, which is R1, right? So I will let others know that I justified this, and others will also say which is the latest justified checkpoint they have. And eventually I will say, not only I know that others think that this is the checkpoint, but others also justified in their local nodes this checkpoint, which means that they also committed to not change it. And if I committed to not change the checkpoint, and if they committed to not change the checkpoint, then we have 2/3 of the network that are already agreed on not changing a specific checkpoint. And that's where I will declare this final, when not only everyone agreed on this, but also everyone committed to not changing it, right? The two-step commit is something that's very common in distributed systems in general. And the basic idea of why we need it is because in the first step, we knew that everyone else was holding that opinion, but we don't know if they justified it yet, because we received 2/3 of the votes for that checkpoint, but I don't know if they received 2/3 of the votes as well. Maybe I received 2/3 of the votes, but they received like half, so they didn't justify. They didn't justify it. And if they didn't justify it, then I have no guarantee that they won't change that. Only I committed to it. So, but if I actually have a message saying, hey, all of them send me a message saying that this is their current justified, they are also committing to not changing it. And when 2/3 of the network committed to that, then that's when we consider it final, right? So yeah, I thought that this friend scene was very appropriate. Hope you also saw the episode. And if not, let's continue to pipelining. So basically what we do, because here we are representing this as 2 steps, right? In the first step, I emit all of the votes for this checkpoint, and then I emit all of the votes for this checkpoint too, but for just like after it's justified. But what we usually do, as you could maybe see here, is that when I attest to both things at the same time. I say, hey, this is the current one, this is the target. I think that this epoch is about this checkpoint, but also this is my latest justified checkpoint. So in this case, what we are doing is that for a single, let's imagine that we are here in this slot and I perform an attestation. What I'll do is saying, hey, this is my target one and this is my source one. This is what I think is the current one, and this is the latest that I already have justified. So if we only perform 2-step commit in the classical term, we would be emitting one finalized thing every 2 epochs, right? Because it takes 2 epochs to finalize something. In one epoch, I justify it, and in the next one, I finalize it. But we are actually overlapping the justification of this one and the finalization of this one. So I potentially, and in the ideal case, I would finalize one block per epoch instead of one per 2 epochs. Which is great. This is called pipelining because we are overlapping the finalization of one of them with the justification of the next one. It's kind of like, how to say this in English? Like an assembly line or a pipeline. So yeah, target is basically, just to review it, target is the one that we're currently trying to justify, and the source is the one that we are trying to finalize, which is the latest justified checkpoint according to myself. Typically, it should be the previous epoch, but sometimes a whole epoch does not arrive to a justified block. So we might have epochs without anything justified. It could be older, the source one. All right. And then this is a terminology thing. We call when we vote T and S at the same time, what we are actually voting for is this arrow here, which is called a link. So S arrow T is my vote, and we call this a link. The reason why we call this a link at all is because it's easier for proofs later on, for proving that this is something that works. So for now, what we achieve with 2-step commit is what we call classic PBFT safety, right? Which is if 2/3 of the network are honest, something that is finalized will never be reverted. And the reason for that is that we exclude anything that's justified from fork choice. So it's completely impossible that something will be reverted. But that's something that's achieved in any classical Byzantine fault tolerance consensus algorithm. Just to recall, Byzantine means untrusted, right? Here what we say is, I think that we already told this in the previous edition, but a Byzantine consensus algorithms is like any blockchain algorithm. You don't trust your peers, so you need to do some stuff, and you cannot provide certain guarantees when there are more than a third of faulty or adversarial validators. But what if there are more than 1/3 of adversarial validators? Where the goal of this kind of finality, and that's where God's power comments come into play, like there's different kind of finalities. What we want is that if for some reason there are more than 1/3 of adversarial validators, we want to impose a very big cost on performing like bad behavior. So they may be able to overturn finality if there are more than 1/3. If there are less than 1/3 of faulty or adversarial, then we guarantee with safety, we guarantee that they cannot reverse the network. But if there are more, they may be able to reverse it at a certain cost. So what we define is two kinds of slashable behavior, right? So there are two, as Ben Edgington says in the ETH2 book, or Upgrading Ethereum, there are two commandments in finality. The first one is that you shall not double vote, and the second one is that you shall not surround vote. Double votes basically mean these kind of things. This is the formal way of expressing it, which means that H we call the height, and the height of a checkpoint is the slot number. So if a checkpoint is the checkpoint number n, then the height will be 32n. But this is a shorter way to put it, and also a more graphic way to put it instead of 32, which is very confusing here in this context. But here, what we have is, so let's imagine that this is our current fork tree, right? And this, instead of this being a slot, let's consider this a whole epoch, because it's simpler, right? We have a checkpoint here, a checkpoint here, a checkpoint here. And let's imagine that I have a checkpoint here, and then currently I have this green vote, right? This is my current view. This is my current justified, and this is my current target, right? What would be illegal would be at the same height for the target to either change the source, which is like this one, or change the target to a different one in the same height. So with this, what we kind of achieve is that we cannot publish a different source or publish like a different branch in the same height, because for it might be the case that at some point in the future, like this is, I'm going to describe legal normal behavior. What could happen is that for this slot or for this epoch, I think that this is the correct fork. But maybe for the next one, my votes changed. Like everything I received from the network has given me different input. So I may change my view, and then I would vote this branch. But what's not legal is to say, hey, actually, in this same epoch, it wasn't this one, it was this one. Because that's basically, it lets you change stuff for free, and that's the thing we kind of want to avoid. It would be logical to change your view if you got more information for the next one, but it wouldn't be logical to emit attestations that are different for the same slot, right? Okay, so for fork choice, we weren't able to do that, but here we specify checkpoints. We say, hey, this is the epoch and this is the root. And so we are kind of able to change that if it wouldn't be for this. And then let me know if you have questions about this. And then we have other things that you cannot do, which is no surround votes, which basically means if you have this link and this link, neither of the links can surround the other one. And we define surrounding with the heights. Like the link S1 and T1 cannot surround S2, T2 like this, or the other way around. It's the same, it's symmetric. So for instance, what does, in a graphic way, surrounding means the following. If I have this vote in green, then I will not be able to emit this other vote in red or this other vote in red. And the reason for this is because if you think about it, here I am voting for targets that are at a different height. So at a different slot or epoch than the one that I had before. So those wouldn't incur in double votes. But at the same time, I wouldn't want this to happen. I wouldn't want, hey, if I was supporting this to pairs, that means that at this point I was supporting indirectly this one. So if then what I'll do is I actually start supporting this. I will say, hey, I actually never thought this was the source. I only thought that maybe this was the target, but I wasn't actually saying that this was the source. So effectively, no surround votes protects people from validators changing their source. Like, hey, I committed to not changing that, but now actually, yeah, this is my justified one. But hey, if this was justified for you before, you committed to not changing it. So this basically protects everyone from validators change, like not committing to their justifications, which was the base of all of this working, right? So double votes basically prevent you from people like ignoring fork choice, and no surround votes prevent free people from validators ignoring their own justifications. Right. And if you think about it, this, so we define both of these behaviors as slashable. And slashable basically means that in classical Casper, in the paper of the Casper algorithm, it says, hey, all of what you own as a validator will be immediately taken away. If you deposited 32 ETH, you will be slashed, and your 32 ETH will immediately be burned, and you are not a validator anymore, which is an incredibly high cost for this. In Casper, which is a combination of Casper and Ghost, or in human words, of Finality and fork choice, what they do is they scale this. Like what they say is, if you will not be fully slashed if you're the only one committing this behavior. But if if you have like a third of the validators performing slashing behavior at the same time, or in a window, like in the last 30 days or something like that, if in the last 30 days, at least a third of the validators are committing slashable behavior, then they are fully slashed. So basically what this means is that your slashable behavior is punished more if more people are doing it, which is kind of the inverse of mob behavior, right? This kind of discourages that if one is behaving bad, then more should be behaving bad, because the more people behaving bad, the more punishment it is distributed along the slashable stakers. So that's the whole idea. And also this is a small detail, but slashing monitoring is external. So I don't know if we talked about this last time, but how is slash performed? Because this is not something that you are able to detect in protocol. Basically, if you pay attention to our code base correctly, you will see, because we haven't implemented some validator features, slashable is nowhere to be seen in the specs. Of course, slash processing is, but emitting slash proofs is not. So basically, we have to have a monitor, which is an external process that every distribution usually includes it in their own consensus client, because it's useful to have that as a validator, and also because performing a proof gives you a reward, so you have incentives to do so. But basically, what you do is you need to include a proof that someone performed one of these behaviors. And that's very simple. Like, for instance, if someone double voted here, it means that this is one of the links that they sent, and this is one of the links that they sent. What I will do is I will tell the proposer validator, hey, proposer, look at this. Here are two links emitted by the same person or by the same validator. And those links are signed by that validator. So it's provable that they incurred in this behavior. So the proposer can then include that in the block, and then everyone can verify that that was a slashable behavior and can calculate the punishment. But the only part here that is not included in the specs is monitoring for slashable behavior and generating that proof. This is an external service. Again, external doesn't mean that you need to run an additional program. Typically, all of the consensus clients include this, and we will do at some point as well. But it's called external because it's not something that's included in the specs. To run a valid validator, you are not obligated to perform monitoring for slashable behavior. You're only obligated to process slashable behavior that's included by the proposers in the blocks. All right. And as we saw before, the reason why this is a gadget is because this is overlaid on top of fork choice, And then if someone justified a checkpoint, then they start ignoring every block for fork choice that's outside, that's not an ancestor of that checkpoint. So basically, as we said before, this is a way to punish people that don't respect their own justifications, and this is a way to punish the people that don't respect their own fork choice when voting for finality. If you actually look, like, we don't have that much time today to go into details. Maybe for part 2, if you are interested in the mathematical proof, but Venegington provides a mathematical, or kind of an intuitive, more than the mathematical proof of why this works. And basically, it mostly relies on this slashable behavior, proving that. Actually, I'm going straight to a conclusion that I haven't said before. So let's talk about guarantees, and then I will talk about the proofs. But basically, in conclusion of all of what we've been talking today, we don't have two kinds of finality. We only have one, but we do have two different levels of guarantees. The first guarantee is provided by the two-step commit, which is that if less than 1/3 of the validators of the network are faulty, then a final checkpoint is final, always, will never be reverted, which is what we want. This is in the happy place where at least 2/3 of the validators are honest, which is pretty common, then a checkpoint will never be reverted. That's awesome. But in the case, and this is where things get tricky, in the case that more than 1/3 of the validators are faulty or adversarial or bad actors, there's absolutely no way that I can prevent them from emitting votes that are contradictory. They can perform slashable behavior. But the good thing is that is slashable behavior. Two-step commit will do nothing about it. But these two slashing commandments guarantee that if what do we want to prevent? We want two checkpoints that are conflicting to be finalized. Yeah, that's something that we want to prevent. That's basically what reversing means. What accountable safety guarantees us is that two conflicting checkpoints are finalized, then at least 1/3 of the validators in order to that to happen, they need to perform an offense. And if they perform an offense, at least 1/3 of the validators will be slashed, which is a huge amount of money and a huge amount of validators. So basically, and this is a quote by Vitalik, so I will just read it out loud. It says, "We cannot guarantee that X will never be reverted, but we can guarantee the slightly weaker claim that either X will never be reverted, or a large group of validators will voluntarily destroy millions of dollars of their own capital." So I just copy pasted this because it was extremely clear by Vitalik. And what it says is basically that we have an extra level of safety in comparison to classical PBFT algorithms. Sorry, PBFT is practical Byzantine fault tolerance. It's a specific algorithm, which is like a very standard algorithm for Byzantine consensus. So the great thing about this is that, hey, I can never guarantee more than I can guarantee. People can make a finalized block be reverted, but if they do so, they will be extremely hardly punished for that. They will lose all of their stake in both of the branches, in the reversed one and in the new one, and they will be basically very hardly slashed. And and the idea is that even if they achieve this, they will not gain from it. They will basically lose a lot of money from it, which is extremely good, because this means that if more than 1/3 of the validators are bad actors, they will still get punished. So there's an economic incentive to not do bad behavior, aside from the computational guarantee, which is the first one, the classical safety. Yeah.
Can I ask something?
Yeah, of course.
Let's say the checkpoint is not getting finalized because the testers, half of the testers says it's not true, half of them are saying it's true, and it goes over epochs, let's say.
Yes.
What happens in the end? It will be justified. The finalized head will be chosen, but how will be the backward compatibility for that will work? Like,
Oh,
because
that's an
there,
amazing question. And that's not covered by this one, but maybe covered in part two. But the spoiler for that is that what you just described is something that finality in itself does not solve, which is what happens if a half of the people are voting for one thing and and the other half is voting for this thing. If that's the case, no block will ever be nor justified nor finalized, and that's a huge liveness problem because we have two competing branches that are not finalized, but they are still there. They're still working there, and depending on which node I communicate to, then I will have uh, different opinions on which is the head, for instance. And that's a huge liveness problem. So the way that this is solved in Ethereum is that imagine that it's not 50-50, it's like 49 and 51, which is still not enough for finalization. There's something called inactivity leak. Inactivity leak is a punishment, a different punishment, and way less than this because it's not slashable behavior. It's just, hey, you're not agreeing, we will all be punished. So it will start deducing small amounts of money from all of the validators' accounts. Like there are several punishable behaviors that are not slashable. Slashable is only like, hey, you're doing something that's completely bad. You're doing something out of protocol. If you're doing this, it means with 100% reason, 100% certainty that you are a bad actor. There are other kind of behaviors like, hey, I don't know, my computer disconnected. I'm not providing, I'm not attesting, I'm not proposing blocks. So I'm not guaranteeing that the network works. That's punishable, but that's not a bad actor thing. That's just bad luck, bad infrastructure, bad whatever. This is very similar. Inactivity leak is one of the punishable but non-slashable behaviors. And what it does is, if the network is not agreeing and not justifying or finalizing, then everyone will be slightly punished and some of their stake is deduced. And how this fixes things? Well, you may ask in two ways. One of them is that theoretically, and this is not a very good justification, there's a better one, people should start agreeing more if you are punishing everyone. Uh, but that's kind of weak, right? That's like very theoretical and very like, I don't know, I believe in people way of thinking. And the other justification, which is more mathematical, is that if you have 49 and 51%, and everyone starts getting deduced the same amount of money, not proportional to their stake, but the same constant amount of money, that means that the total stake will change. So the proportions will start changing, and the 51% will start growing and growing and growing, and the 49 will start shrinking and shrinking and shrinking. Eventually, if that continues and nothing else happens, like typically in activity leaks, and these kind of problems are more related to bugs than related to bad behavior. Like there's a bug in some kind in one of the clients, and that client might be a big client, so they are not performing fork choice correctly for a very, very specific edge case, or I wouldn't say correctly, they are performing fork choice in a slightly different way than the other ones for a very specific edge case. That's why inactivity leak typically happens. Well, what would happen is that eventually stake will start getting reduced for all the validators, and the ones that were performing, like having most of the stake, will eventually reach 2/3, and then it will be justified and finalized for those ones. That's if not, no one performs a fix, because fortunately in real life, what happens is that people start getting punished, and then everyone gets desperate to fix the bug in their clients, whatever it was. So typically, like I don't think that we ever arrived to that horrible place where everyone starts getting punished and punished and punished until the 2/3 arrive. Yeah, I think that in all of the cases in the previous inactivity leaks, the bug got fixed at some point, and then justification and finalization happened again. So yeah, we will not talk
Yeah.
about. Yeah, sorry, go ahead.
Okay. Sorry, I just wanted to ask a follow-up question. So you said that if there was a scenario where 49% are agreeing on a particular point and 51% are agreeing on a different point, you said that if they are being slashed at a constant rate, that one would get um, the spread would become wider. I
Yeah,
don't like. It's not. I'm not kind of understanding the maths because it's constant and it's more like you're reducing So can you explain that a bit? Or it's...
Of course, imagine that you have a stake of 3 abstract units, but you have 3 and I have 4. And then we both get deduced 1. Now you have 2 and I have 3. And then we get deduced 1 again, and you have 2 and I have 1. Sorry, the other way around. You have 1 and I have 2. So now, before we were almost half and half, and now I'm 2/3 and you're 1/3. Because we are deducing at constant rates, not at a proportion of each one's stakes. It's not like I'm saying, hey, you get deduced 5% and I get deduced 5% of my stake. We all are deduced at constant rates that are exactly the same for everyone. And when you do that, the ones that have the bigger stake tend to have bigger proportions in time, even if everyone is punished the same. Does that make sense?
Yeah. So basically, yours, the person with the higher, with the lower, on the lower side, his will finish before mine. So automatically,
Yeah.
ahead.
Basically, like the ones that have. Sorry, go ahead.
No, you can go. I just want to ask another question. Finish.
Yeah. No. Yeah. What I was saying is that basically what inactivity leaks does is that eventually, if no one fixes the bug, what will happen is that the ones that had the bigger stake will have big enough proportions so that they are now 2/3.
Yeah. So you said that in a situation whereby there is more than 1/3 of the network that are bad actors. So after they get slashed, so I'm assuming there's a mechanism to still fix, to still reconcile things even after they get slashed, or does it just continue like that?
Well, what happens is that if they were so that's a good question. Like, hey, okay, I slashed these people. Now what happens? Basically, what happens is that effectively they were able to revert the fork. That happened. Like they were able to revert a finalized block, and then now we are on a new branch with a different finalized checkpoint for that same height, and we continue working. But all of them got immediately slashed, so they are not validators anymore. So now, from the present and into the future, if there are no more bad actors than them, we will only be working with good actors. Or if they want to participate again, they need to deposit 32 ETH again, 32 new ETH, which is a lot of money, man. Like I don't have that amount of money just available for this kind of stuff. So either they are like extremely, extremely, extremely rich and they can participate again. But even if they do, like if they perform this even once again, they incur in like gigantic problems. So, and this is all while all of the other mechanisms still work. Like fork choice is still working, block validation is still working. Like this doesn't mean that they can put any block into there. This only means that they can like outvote the fork or something like that. It's they can change their opinion on something in a non-valid way, but like all of the blocks are still valid. And this is something kind of important, which is not always talked about, which is even if I perform a reversal, that doesn't mean that the other blocks will not contain the transactions that I have, because the mempool is still kind of the same in all of the execution nodes. So it might have slight differences, but typically the blocks that are produced in different forks will also contain almost, if not all, of the same transactions, because they are based on the same mempools typically, unless we're like performing some very heavy MEV or that kind of stuff, which also is something to talk about, which is completely out of our scope, even in this project, right? But you kind of start getting to way harder stuff. So basically, this is an extremely high cost for not so much gain, typically. And that's why it works so well. Like you really don't want to spend 32 ETH on reverting to another branch that may even have maybe the same transactions. So yeah, it's kind of the issue. Like you still need to be a proposer to propose a block, and this doesn't change that in any way.
Yeah, I think this just shows that economic security works way, way better than many mathematical proofs because no one wants to lose money and everybody's
Well, it's a great thing to have both. It's a great thing that you have mathematical, and on top of that, you also have incentives to not do this kind of stuff, and you're not trying to break it because the price of breaking it is extremely costly. So yeah, and yeah, if I think this is a proof of anything, it's a proof that economics matter a lot. Like sometimes someone coming from a more academic perspective might say, hey, this is still not a guarantee. Like this could happen, but we still live in the real world. Like we are still trying to prevent real people from doing stuff. That's our final goal. So if that's the case, then having some real incentives for real people, it's still a valid way of preventing that.
Yeah. Not a lot of people have that kind of money to spend on something that probably won't have.
I would say very, very little amount of people do, and even if they did, they wouldn't be able to perform these like many times.
Yeah.
All right, so that's the end of today's slides, which is nice. I'm happy that I didn't put more stuff into it because it's already 10 a.m. here in Argentina. So we will be in 45 minutes here. My idea is having a part 2 eventually at some point next week. Not Thursday because we have the community call, but at some point next week. And we can just talk about how this is implemented in code, which is something that we didn't get the chance to talk about today. And to like review the epoch processing section of Finality and relate these that we talked today to that, which I think it's a nice exercise. So yeah, I will send invitation links afterwards and we can continue with that. Do we have any more questions about any of these? I can go back to any of the slides and we can continue talking about anything.
Yeah, so I just wanted to know your thoughts. So I was assuming that if you get slashed for like if there's a scenario where 1/3 of the network, more than 1/3 of the network says is voting on the wrong thing and they get completely slashed, there should be a mechanism that stops them from coming back again. So, but what are your thoughts? Do you think it makes it that's a sense? I don't know if I call that censorship, but it kind of blocks some people. But it kind of makes sense that if someone is trying that hard to stop the system, there should be a way to stop the person from coming back. What do you think? Do you think it's?
I think it's a very good question, but I think it's a very complicated issue as well. On the one hand, this is immediately done because when you're slashed, you're not only deduced this amount of money, but your validator is effectively banned from the validator set. So you cannot, with the same keys, start a new validator. You need to start a new one because your keys are your ID, right? Your public keys are the identification of your validator. So if you try to like bring up that validator again, you will be essentially depositing money in a validator that's slashed and it won't work for anything. So you'll be wasting your money again. So effectively that happens, but what you will probably say, which is true, is, hey, yeah, but nothing prevents me from creating new keys and getting in the network again. And basically, like, well, I need to deposit 32 ETH again, which is an extremely high cost, which we already talked about. But theoretically, it would be nice that something prevented me from ever joining the network again, even with different keys. And I think that sparks a completely different discussion, which is identity on chain. Like one of the whole reasons that we have civil resistance mechanisms like proof of stake or proof of work is to prevent people from starting infinite nodes and infinite votes in these kind of systems, right? That's one of the Byzantine base problems. For not only Byzantine, but also anonymous chains. And you basically don't have many alternatives. There are a lot of alternatives, but not currently. For instance, you could have a ZK mechanism to prove that you didn't have a validator before or something like that. But it's still not trivial because I don't know if you can prove that you didn't do something. You can prove that you did something, but I don't think it's possible to prove that you didn't appear here before. So then you start having other discussions like Gitcoin or that kind of stuff, like identity, like actual identity on chain. And you could have, hey, you're anonymous, but I know that you are a person. I don't know if that's the way we want to go, but it's one possible way to go. And that could work, for instance, for other kinds of blockchains, not Ethereum, but maybe if a government had a blockchain that was public and free for all, but you have to be a citizen of somewhere, for instance, and you need to have a proof of citizenship, even if that proof doesn't reveal your identity, which is something that could be achieved with ZK. And that may be useful for this kind of stuff, like, hey, you perform a slashable behavior or you're out of the validator set. But also, if you have something that is your right as a citizen, you probably don't want to do that, or not in that way exactly. Yeah, so it's an infinitely long and interesting discussion, a bit out of scope. I love to discuss it though, but I don't think it's an easy thing to solve. It's not something that like we can figure out in like 10 minutes.
Yeah, something I just thought about is what if like people could vote of you becoming a validator, then people can have more time to really go into if you were a bad actor before. But yeah, it's just it's
Yeah.
theoretical, probably not practical. But yeah, those
Yeah. Yeah, it's a very hard problem. Like identity on chain is a very hard problem in itself. So I think that kind of the reason why the whole ETH community went, like Ethereum community went this way, is that, hey, if we cannot prove that people are different people or the same people, at least we will make them pay extremely high amounts of money for bad behavior. And that's enough for people not want to do this thing repeatedly. Like even if they did it once, that's terrible. So I think it's a good compromise, even if it's not like a mathematical thing. All right. Do we have anything else?
No, it's very well clear.
Awesome. Okay, thanks, guys. Thanks for being here. We'll probably do part 2 on Monday or Tuesday, depends. I will send invitation links or a doodle or whatever. Yeah, thank you for joining.
Actually, we can we make something like edge cases that happened earlier, like the history of consensus clients.
Or like history of inactivity leaks and bugs and that kind of
yeah,
stuff.
yeah.
Oh, I
Actually,
like to do that actually.
I've read some in the E2 book when I was working on the state transition ones. There are some interesting ones, so we can like make a workshop on that as well, if it's possible.
That sounds very fun. I will try to include that. Like I will first go to the code, but I think that the code is very short, so we can cover it in a very reasonable amount of time. And then afterwards, we can focus on the history of things going bad, which is also a very interesting topic because it allows you to see, like when you talk about the happy path, you're always very trusting of the code. And then you see things go bad and you say, hey, this wasn't a perfect protocol. Something happened here. Someone had a bug and this happened. But you also see like the safety mechanisms working, which is also very interesting. Like, hey, inactivity leak happened. It's a very interesting thing. And it kind of worked in the way that everyone started fixing the bug afterwards. So yeah, let's definitely talk about that if we have time.
All right. Thank you for the explanation.
Of course, guys. Brilliant to have you here. See you next time.